So we know that at least continuous functions, which are defined on closed intervals, should have a maximum and a minimum value. They do, according to the theorem. But the theorem doesn't actually tell us how to find them, how to find those maxes and minimums. So let's take a look at a picture and try to figure out something that is common to all of these extreme values. Well, here is a graph in blue, and it's got a maximum here, it's got a minimum here, and both of these coordinates, here's the coordinate for the maximum, well, the tangent line to that function is horizontal there. And over here, the tangent line to the function at this minimum point is also horizontal. So maybe it is that extreme values always have the tangent line being horizontal. Well, here is a more technical way to say that. Fermat's theorem, Fermat's another mathematician from a couple hundred years ago. If a function f does have a local minimum or a local maximum at some coordinate x equals c, and if the derivative of f evaluated at c actually exists, then f prime of c has to be 0. So yes, a 0 slope, and yes, a horizontal tangent line. So what this means is that derivatives can help us identify maximums and minimums, right? But we need to be careful about which way the implication goes. So every local max or local min has the derivative of the function there equals 0 if that derivative exists. But we have to be careful of false positives. So let's look at f of x equals x cubed. Its derivative is f prime of x equals 3x squared. And this derivative is only equal to 0 at x equals 0. Is x equals 0 a maximum value of this function? No, it's not. I just look at the picture here. 0 cubed is 0, and there's plenty of places on the graph where the function was greater than that, even nearby, right? If I'm really close into 0, there'll be some positive numbers to the right of that. They will cube, and they'll still be greater than 0. And 0 is not a local minimum either. No matter how far I zoom in here, there'll be some negative number included to the left of 0. It will cube and still be negative, which means that 0 isn't the smallest value of this function there either. So 0 is not a local maximum of this function. 0 is not a local minimum of this function. The derivative here being 0 was a sort of a false positive. Now, what this is saying is that the function does have a horizontal tangent line there. All local minimums and local maximums, if they have a tangent line, that tangent line will be horizontal, but not all horizontal tangent lines are indicative of a maximum or a minimum. So this is something to be really careful about as to like what means what else. Maximums and minimums, at least local maximums, local minimums, always have a horizontal tangent line, so long as the derivative of that function exists. Horizontal tangent lines and derivatives being 0 does not automatically mean that you have a maximum or a minimum, just a potential maximum or minimum that we then gotta do a little bit more work to figure out. Now, I keep saying this business about if the derivative exists. We've seen functions whose derivative fails to exist somewhere. Here's the absolute value function. And it does not have a derivative at x equals 0, right? If I went to calculate a derivative there, the limit does not converge. Remember, every derivative is secretly a limit. We just have nice formulas so that we don't have to calculate limits every single time. But the absolute value function is not differentiable at 0. So I don't have a tangent line at x equals 0, but x equals 0 definitely is my minimum there. The smallest absolute value that any real number can have is 0. And every real number that's not 0 has an absolute value which is greater than 0. So this is the minimum, but derivatives wouldn't have helped me there. At least not looking for the derivative equal to 0. So how can I fix this up where I'm saying that I kind of want that derivative to be 0, but sometimes my derivative won't exist. And sometimes the derivative will be 0, but I won't actually have a maximum there, or I won't actually have a minimum there. So how can I fix this? We are going to have a new classification for our coordinates. So if I have some x coordinate so that the derivative of my function is 0 at c, c is my x coordinate, or the derivative of the function does not exist, then I'm going to call this c a critical number or a critical point. And critical here just means important to look at. These are the potential maximum and minimum values, maximums and minimums of the function. So what I'm saying here is that all local maximums and local minimums occur at critical points of the function f. So if we are interested in finding these things, we would like to find critical values. So what we're going to do is we are going to calculate the derivative of our function, look for all the possible coordinates that could make that derivative 0, and look at all the possible coordinates that could make that function, that derivative, not exist. So this gives us a 3-step process to finding absolute maximums and absolute minimums. Either the absolute extreme value, whichever kind it is a local maximum or a local minimum, or it could have been one of those endpoints where we have chopped off the function. We can't detect those with derivatives. So step number 1, we're going to have all the critical values of our function, and we're going to evaluate the function at each one of those critical points. Step number 2, we are also going to calculate f at the 2 different endpoints of the interval. And then out of all the numbers that we saw from steps 1 and 2, the largest number on our list is the absolute maximum of the function. And the smallest of these numbers is the absolute minimum of the function. That's it. And so it really is crucial here that we are able to calculate derivatives, that we are able to tell when is a derivative 0 and when does a derivative fail to exist.